Hi, my name is Dr. Mantesh. Today we'll see the experiment related to VLSI laboratory 21 ECL 66. First experiment is about 4-bit adder. Since they did not mention which type of adder, so we can simply go for ripple carry adder, 4-bit ripple carry adder, which is the simplest one. The experiment says we have to write a Verilog code, verify the functionality using testbench, and synthesize the design by setting proper constraints. And what we are supposed to do is we have to identify critical path, maximum delay, total number of cells used. If possible, we'll see how to calculate area and power. So let's get started with Xilinx. So I just open Xilinx 14.7, go to File, New Project, and you choose the directory. So I'm trying to save here. Okay, so you give a 4-bit adder, 4-bit RCA, 4-bit, something like that. So this is the project name. You can give description here. 4-bit ripple carry adder, something like that. Next one, you are supposed to select the hardware and software. Check which hardware and software available in the laboratory. So we have this Spartan 3, XC3S50, PQ208. So this is Spartan 3, 50 kilo system gates available. PQ208 is plastic quad, 208 pins. The speed grade is 4. Even 5 is also available for selection. So you choose Verilog code because in the curriculum they mentioned about Verilog code. You are not supposed to use VHDL. So write Verilog code and keep remaining things as it is. Say next. This will give summary. Say finish. This creates projects. So this is the project, and now you are supposed to create new source so that you can write Verilog code in there. Either you can go to project, new source, or shortcut is there, new source. So here you are supposed to take Verilog module. You write say adder 4-bit or RCA 4-bit, something like that. So say add to project, this must be checked. Suppose if you are writing code starting from the scratch, you have to give what are the inputs and outputs. Since I have the code written already ready-made and I have saved in my directory, so this is the code that I have. So I simply, or you can type these things, A, B, C in, S and C out. For example, A is 4-bit, B is 4-bit. Okay, you can select something like this in the examination, or while writing sum you write. Here you mention output, which is a 4-bit, 3 down to 0, 3 is MSB. Similar to that, you can mention scene, which is input, which is not a bus, it is simple bit, C out, something like that. You can select and you can hit next, which will give the ready-made things like this. Okay, then you can simply write the code after this. So at this moment I have code, so I don't want to type it again. I'll simply select everything and paste it with my code. So this is the code, simply save it. Now what this code consists is two things. One is there are two modules, you can see. This is full adder. This full adder consists of A, B, C, sum and C out. The data flow model or equations sum and C out are written something like this. And then this module full adder, you are trying to call it in the main module. However, you can write the main module first and full adder at the last. Still it works, doesn't make much difference. Or you can write two different modules or two different sources, one for full adder, one for 4-bit adder. So there is an assumption that you know about 4-bit ripple carry adder, how carry propagates and everything. So I am not going to discuss anything in detail about that. So that is the assumption that I made. You know about 4-bit ripple carry adder. So this is how the instantiation is done. 4-bit full adder is the name, FA1 instance name. Then you are giving in the same order A, B, C in S. So don't change the order, or else there is something called as implicit bonding that can be done. So for example, if you want to write scene first, you can write scene is connected to scene by assigning it clearly. Next one, you are taking the second instance of full adder and you are binding it for second full adder, third full adder, fourth full adder. At the end you are trying to bind it with C out. The first one is C in here. C. So remaining things are signals or wires. In this Verilog case, these things can be simple wire. So wire C1, C2, C3. So this is all about program. I would like to simulate it. Without even test bench, we can able to simulate it. So come to simulation and then you can give input directly in the iSim, which is Xilinx simulator. So you can give input. This is an explanation only, but according to the curriculum that is mentioned, you are supposed to write a test bench. Okay. So without test bench also can be done. That is what the intention of the tutorial. So I want to add 4 plus 5. Apply. Okay. Right click, force constant. You can give binary or you can mention unsigned decimal. For me, everything is equal. I know every radix, so I don't want to differentiate. So simply I am making carry in as 0. So 4 plus 5, now I should get 9. Okay, after running, run for, or you can go to simulation, run for specified time. This one, our shortcut is here. So I got 9. 4 plus 5 is 9. So you can change the radix to, so 4 plus 5 is 9. You can add any numbers, any 4-bit numbers, any two 4-bit numbers. And also you can give carry in, you can check whether carry is generated or not. So this is all about simulation without using testbench. At this point I would like to go for testbench. So I have a testbench, or you simply take new source. Since you are doing it first time, so you are supposed to take new source, type header -bit underscore test, something like this. And I have ready-made code, so I don't want to do anything here. Go to header test. Control A, Control V. So this is about testbench. Okay. So I have written testbench now. As soon as you save it, the testbench will be top module, and your adder1 will be as an instance. It will be called here. So where is that adder1? Here. This is called, and these values are assigned. So input values are also given here, 4-bit, 3, and this is 7. 7 plus 3, 11 I should get, that is B. Another value given is B plus 7. So you may get some carry there. So as soon as you click on top module and simulate behavioral model, so you click on default with WCFG. So the two values that are given will appear, that is one value is this, another value is this. Better to sort out with A and B. A, B, C in and C out. So this is the simplest way. Okay. So now check for inputs and outputs. And if you wish, you can change the radix. B value is common in both the values. Now in one case, the carry will appear. So this is all about simulation. That is verification of the functionality. Okay. Second part is we are trying to synthesize the design. We don't have any constraints to give now in the Xilinx. However, if you are trying to use cadence, RTL to GDS flow, you can give constraints. Now it is not possible. You can find critical path, maximum delay, and total number of cells. So the first thing you are supposed to do, from simulation, you are supposed to come back to implementation. From simulation, now I entered into implementation. Just remove the test bench, remove it. This may disturb the synthesis flow, so I am removing it, and then synthesize XST. As soon as you do it, you can see everything, all the simulated synthesized hardware and how much it is and everything. You can able to see here, or if it is closed by mistake or something, you click on design summary, or there is another shortcut here, click on design summary, click on design summary, still you can get it. Next, here I am trying to observe the first thing, that is I am going for synthesis report. Double click on it. Then first thing I would like to identify the critical path. here the critical path starts from B0 and ends with C out is the critical path that you can note it down, and the maximum delay of that is around 13.902 nanosecond, and these are the two tasks, that is critical path and maximum delay. Okay, next thing is total number of cells used. Total number of cells. You go for summary, and here you can see how many cells used. Number of slices 4 out of 760. Okay, hardly 0%, less than 1%. So these are the number of cells that we have used. Okay, you can see that device. See that in the device utilization summary. Also, same can be observed in the synthesis report. Synthesis report will also show that. Okay, what all used. See, the same thing can be observed here. Which device and how much percentage of device is utilized. So it is less than 1% of the total slices, total hardware, but we are using IOBs, input-output bonding pads. So this is about this is about total number of cells used. The power requirement and total area can be observed in Exp1 analyzer. You go to implement design. Since it is too small, as we already observed, the total size of the design itself is less than 1%. So only static power can be observed, not a dynamic power. So it's just static power of this FPGA. I am talking about static power of FPGA, not static power of design. So this can be observed in Exp1 analyzer. So expand. So what I did is expand implementation. In that expand place and route, and click on Exp1 analyzer. If your design is big enough, say 25, 30%, 50% or 100% of that FPGA capacity, then you can get dynamic power as well. Static power is simply called as leakage power. Dynamic power, you know about the formula of dynamic power. It is CV square F capacitance, and it depends on voltage and frequency. So it takes time. In that you can able to see only leakage power, which is called as static power. Okay, so nothing. This can be adjusted. If you change the device, this will be different. Also, if you change the device, as you can see, there is no dynamic power. Okay, no dynamic power. So because the design is too small. So this is how to observe the static power, which is about 0.027, that is 27 milliwatt. Next thing, if you change the device, the delays, the maximum delay or critical path, what we observed, everything will change. Okay, so just be careful, don't stick to this, because this device will give around 29 seconds, whatever we observed. Okay, so this device gave us maximum path delay, critical path delay of 13.902 nanoseconds. Suppose if you change the hardware, for example, say speed grade 5. I don't change the hardware, just changing the speed grade and synthesizing it again will give a different delay. Now it is 13.902 nanosecond. We'll observe it again. So synthesis completed. You can refresh it. Anyhow, it will update automatically. So you can observe that it is less than the previous one. Previous one it was 13.902 nanosecond. Now it is 12 nanosecond. So it's based on your device, based on the code that what you have written. Okay. This is all about first experiment. Thanks for watching.